Okay, in this episode, we are going to add Midi support to the Subtractive Synth. We already have seen the demonstration and how it works. Our Subtractive Synth is following this architecture. We've seen that in the previous video. So we've got VCO, VCF, VCA, and we extended the architecture a little bit, a tiny little bit. So we revised our first synthesizer, and here's the revised version. What we can see, we've got our synth here, quite normal. What we've have done is that in line 19 and 20 we defined two saw oscillators, and instead of doing multi-channel expansion, we have these two saw oscillator, and we are just adding them together here. So the data is going to be generated at audio rate, so the audio loop is running here, and so we are adding them up, and as 1 plus 1 is plus 2 and minus 1 plus minus 1 is minus 2, we need to normalize it, and we do this by dividing the values by 2. All right, this is a bipolar signal, so it goes from minus 1 to 1. So and the rest is pretty simple, pretty similar to the earlier version of the synthesizer. I just added a little factor down here to make the synth really soft. It's always very dangerous to have too high of a volume here. Okay, this is not really actually needed. I'm just very cautious there. Okay, and then there are two more things that I added, and this is these two lines here, 11 and 12, and I specifically named the stuff global release and global VCO2 detune, and from the names you can get the function of it. This is a global variable that stores the release time for the synthesizer, and this is a global variable that stores the amount of detune for the second VCO. And as you can see here, down here, these values are going to be used, and detune 2 will be set to the initial value, which is 0.01. Okay, and later on we are going to change these values. So this is the revised version of our Subtractive Synth, and now we want to add Midi support to it. So we want to use a keyboard to play the synth. So what is Midi? So Midi is the Musical Instrument Digital Interface. It's an acronym, and it's been a technical standard defined by many people, but the core names are Kagehashi and Smith and Wood. Here you can see the Midi definition in Wikipedia, and it goes on and on and on. And then just to show you, here's Dave Smith. You might know he is here with sequential because he's a synth designer and has designed very famous synths like the Prophet 6. All right, and they came up with the idea to kind of like connect synthesizers together in order to synchronize them. Actually, the idea came from Tom Oberheim, but as Smith has worked for Oberheim before, and he the idea was kind of like in the open space. And very fortunately for us, they then decided to create an open standard that allowed multiple brands to be speaking to each other. So the technical standard allows us to connect synthesizers and keyboards together. So it defines very many aspects. It's a communication protocol, it's a digital interface, it also defines the electrical connectors, it's a file format, and so on and so on. There's quite a lot that is defined within the standard. So the electrical connectors that you might have seen, they might look like this. You know, these are the DIN connectors, and when you have a look at some older keyboards, you might be finding these kind of cables. And nowadays, most of it is done via USB. So Midi allows us to connect musical instruments, and musical data is going to be sent. This is digital data, and it's not audio data. What is sent is note numbers, velocity, or control data, amongst others. There's more that can be sent, but usually note number, velocity, and control data is the most important part. And the note numbers are defined according to the position of the key on a keyboard. And within the English kind of like culture, it's normal to name the C1 the middle C. And this middle C, which is positioned in the middle of the keyboard, is getting the note number 60. So, and then it goes all the way down to 1 and all the way up to 127. All right. Now, MIDI is able to talk on 16 channels. That is, you can more or less connect 16 systems through a single cable or a daisy chain of this cable, and talk to all these 16 devices, which is pretty cool. So, as I said, today mostly MIDI is kind of like used via USB, which is very convenient because you can simply stick it into your computer and the system is going to be connected. It also is provided with power, so that's very, very nice. And of course, USB is much, much faster in general than the very old standard from the 1980s. But it is still also possible to work with DIN cables, these DIN cables, which I just showed you. And from time to time, this has some advantages. And we are going to use these cables and adapters when we are going over to hardware synthesizers, so leaving the computer, but going to microcontrollers. And these quite often use the old cable, the old standard. All right. So now let's try to understand how this all works in SuperCollider. First of all, we need to connect our MIDI device. We've seen that I'm using this KeyStep Pro, and this is very simple. SuperCollider provides us with an object called MIDI in, and this one has the message called connect all. And if you send off the message connect all, then the server is going to connect to all MIDI input devices that are currently found on the bus. And so you don't need to take care about any number or anything like that. Any device that is connected will be able to talk. So, okay. Once you've kind of like connected, then you need to process the data, and this is done with a very central concept. It's done with callbacks. So nowadays this is sometimes also called reactive programming, depending on where you are. But what you basically do, you have events that you react to. So one event obviously is that you press the key, and the key is press is separated into a node on and a node off event. So once you press it, you get a node on event, and once you release it, you get a node off event. And as you can see here, the MIDI node on function has a functional object, functional parameter. A functional parameter means that you're not handing in a value, but you rather hand in a function. And in this case, it's an anonymous function, which you can see here, defined by the curly brackets. These are the arguments. So in goes the velocity, how fast you press the key, how loud the key will be, and the second one is going to be the note number. Which key did you press? And now the magic happens, because now we are creating a synth, and we are taking the data that is sent via MIDI to configure the synth. So one more concept has also been introduced, namely we want the synthesizer to be polyphonic, and in order to be polyphonic, we basically need an oscillator or a synthesizer for each of the keys that we press. And in order to do so, we defined a MIDI sample array, an array with the size of 128. You know, there are 128 possible MIDI notes that you can press, MIDI keys that you can press from 0 to 127. We define this array, and within this array we store the generated synth. So it stores synthesizers, and as you can see, the node number is the index. So if I press the middle C, I get a node number of 60. So we take the position in the array of 60, so the MIDI sampler array at position 60 gets a synth, and we are using the synth definition that we've seen, the supersaw, and now we are giving it some parameters, and obviously we need to define the frequency, and the frequency is obviously depending on the note number. Now the note number 60 is not the frequency of the middle C. The frequency of the middle C can be computed from the note number by using the function Midi CPS. This stands for Midi node to CPS cycles per second. So if you just send the 60, the middle C, then this function is going to give you 261 and a little bit hertz. If you're giving it the A1, then it's going to give you 440 hertz. So that's very convenient. You don't have to do it yourself. Just take the note number and convert it into the frequency. With the amplitude, something quite interesting is happening here. So the velocity is taken, and this is a mapping function. And this is a mapping function that goes from linear to linear. So it basically maps the interval from 0 to 127, which is the values that the Midi is using for defining the velocity, and maps it to the interval of 0 to 1. So 0 is going to be mapped to 0, and 127 is going to be mapped to 1, and if it's 64, then it's going to be mapped to 0.5. Okay, and for the release and the detune, we are taking our global variables. So we've got the state of the synth, and it's stored within these two variables, and these will later be used and will then be kind of like manipulated with control messages. This is this thing that we see later. Okay, but what is happening when the key is left? Well, if you kind of let go the key, then we will get a node off event, and the node off event is just the same thing. We've got a functional object, velocity and note number, and now the following happens. The MIDI sample array at the node number, we are going to set the gate to 0. We've seen that in the last video. The ADSR envelope generator, once it gets a gate of 0, then it knows that the key has been let loose, so there is no longer pressed, and therefore the ADSR is then running to its end, so the release phase is going to be ended, and eventually once this is ended, very happily for us, or very luckily for us, SuperCollider is going to throw away the synthesizer, so it's going to erase it from memory. In order to make this really happen, we also set the array to nil at node number, so that we know that the synthesizer is no longer usable. All right. So every time we press a key, we generate a new synthesizer. Every time we release the key, this synthesizer is going to be stopped and is removed from memory. Okay. So in order to define an interface and using knobs to control the stuff, we are using control messages, and these control messages will be processed by the CC. And once again, we've got a functional object. Now this time we got three arguments. First is the value, second is the CC number, third is a channel. So these messages, just like the other media messages, will be distributed according across some channel. Channel number will be 0 to 15. The value is the value that is going to be sent, and usually again the value will be between 0 and 127, and the CC number, this is the number of the knob. Each knob gets a specific number, and now this crucially depends on the device you are using. So I've got two devices here, for example, a Lasys keyboard and the KeyStep Pro, for example, and they differ. They've got different knob numbers, kind of like. So in order to define the interface, you need to adapt to the specific device. So as you can see, I'm reacting to two knobs here. One has got the CC number 74, the other one has the CC number 75. And so what I did, I said, okay, I'm using knob 74 for the global release and the other one for the detune. And you see, then I'm mapping again these values from 0 to 127 to 0 to 5. So the maximum release that we have is 5 seconds. And I'm mapping the value for the detune from 0 to 127 to 0, almost 0 to 0 0.5. But I'm not doing this in a linear fashion, but in an exponential fashion, because then I get more control in the finer values that we have. And then I also print out DT, Q, and GR to give me some visual feedback that I actually turned the thing. Now, one thing has to be is left to be done, and this is we need to update all the synthesizers that are currently running. So what this is done here, it's a loop, it's running through all the MIDI sampler array, and if the synth is not nil, that is, if it's still there, then release and detune of the synth is going to be set to the global values. So if I'm pressing 4 keys, then 4 synths are going to be vivid, alive in the array, and these 4 are going to be set. All right, so this is the way a polyphonic synthesizer can be implemented in SuperCollider, and we will later see that it is quite similar if we are using other formal devices. So come up to the conclusion. SuperCollider provides us with support for processing MIDI data. We've seen 2 objects, which is MIDI in and MIDI dev. There are more, but MIDI in and MIDI dev is very simple. In order to process the MIDI data, we have to define callback functions. These callback functions will be called depending on the events that we are listening to, so key press or key release. And the state of a synth, namely more or less its configuration, its current configuration, or its sound definition, can be stored in variables, and we've seen that we are able to use variables, global variables, which we define with this tilde in front of the name, and then we can simply use it inside our sketch. In order to implement a polyphonic synthesizer, we use an array. And the idea there is for each MIDI node number, a synth is going to be defined, and this is going to be happening when the key is pressed. Okay, some final thoughts as usual. The concepts that we've seen in this tiny examples are very common in many music programming frameworks. You will see them again and again. If you've understood what I've told you here, then you are doing a great and big step into the next into the other frameworks. We also have seen that a synthesizer is a real-time system, and in a real-time system, the system has to react in real time. That's why it's called real time. And in a synth, a number of loops run in parallel. So there's a MIDI loop, and the MIDI loop is there to receive, send, and process MIDI data. So constantly it's running, and looking for MIDI data. Then, of course, there's the audio loop, and the audio loop is there to generate the sound. So it's running, and constantly is processing the data and providing the speakers with sound. And there are more loops, but one which is quite important is the control loop. The control loop usually runs at a lower rate, so the audio loop runs at top speed of 100 samples per second, or whatever frequency you've got installed on your system. But the control loop usually runs a little bit slower, but it's there to process data that controls aspects of the synth state. And we are going to see this later when we are working with real hardware synthesizers. Okay, so far for our episode 2. Thanks for listening, and see you later.